What we're going to talk about today is called hybridization. The idea here is a mixing of orbitals, right? Because that's what hybrid means. It means to mix things. So if you're an organic chemist and you're thinking about the very simple molecule methane, C with 4 H's attached. Now, molecular geometry tells us that this is a tetrahedron. Every single one of these bonds is identical in bond length, and every one of these angles has an identical bond angle. Essentially, it looks like there's my carbon, there's a hydrogen here, there's a hydrogen here. All three of these are in the same plane. There's a hydrogen coming out at you, there's a hydrogen going back in, and every one of these bond angles is the same. Well, if you're an organic chemist and you're thinking about how that bonding works, carbon's valence electrons are 2s, 2p, they look like that. And then if you think about the hydrogens coming in and bonding, maybe they go here and here and here and here. Well, that doesn't really look like they should be 4 identical bonds and 4 identical bond angles. What you'd really want for that is this: 4 identical orbitals, each one with one of the carbon electrons, and then the hydrogen electrons coming in like that, for the purple ones. Now that you would expect to be 4 identical bond lengths and 4 identical bond angles. So to an organic chemist, they would much rather have this than this. So the theory goes that for things like carbon, the s and the p orbitals mix together to create a new kind of orbital that would give us something like this. Now, how does it do that? Well, here's my s. Here are my 3p. Remember, the p are all the same shape. They're just in different angles in the world. The idea is these 4 orbitals mix together to give me 4 new ones that look like this. Once again, they are all identical. They are, in fact, all in different orientations in space, which I'm not going to try to draw. If you think about what a tetrahedral looks like, that's the orientation in space. These are nodes. Remember, nodes are places where there are no electrons, and you can kind of think of them crossing at the nodes, and that being where they all cross, being the nucleus of the carbon. But these things here are what I represented with 4 dashes on the previous screen, and each one of those would have 1 carbon electron. Now, since it's a mixture of 1 s and 3 different p's, these are called sp3 orbitals. There are 4 of them, but they are all called sp3 orbitals. So if we're talking about methane again, here is one of those sp3 orbitals, and here is my s orbital that is from the hydrogen, and that overlap of orbitals, that's the bond. That's the bond that I represented before as this. This could also work between 2 carbons. So I might have an sp3 here from 1 carbon and another sp3 here from another carbon, and again that overlap. So that might be a carbon-carbon bond like that. Okay? These are called sigma bonds. Okay? This head-to-head overlap, where at least one of the orbitals in the bond is a hybridized orbital, that's a sigma bond. Now, according to this theory, of this bonding theory, there is exactly one sigma bond between any two atoms. Okay? Exactly one sigma bond between any two atoms. So if I said to you ethane, C, C, H, 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 every one of these bonds is a sigma bond. That's the Greek sigma right there. If you want to see that on your computer screen, it's an S in symbol font. It's called a sigma. And there's one in between everything, which is all very well and good until we think about double bonds or triple bonds. Suppose instead of ethane, I had ethene, this thing. It's still true that there is exactly one sigma bond between everything. Which leaves me with another bond, doesn't it? Leaves me with this bond. What kind of bond is that? Okay, we have to expand our theory a little bit. This thing is called a pi bond. Now, this has nothing to do with 3.14. That's a different pi. This is a pi bond as opposed to a sigma bond. Any bond that's not a sigma bond is a pi bond. So a double bond is made up of a sigma and a pi. A triple bond is made up of a sigma and two pi's. Okay, there's still exactly one sigma between everything. Now, what is a pi bond? A pi bond is a side-to-side overlap of two unhybridized p orbitals. Okay? So here's a p on one carbon. Here's a p on another carbon. And that overlap there, that's my pi bond. As opposed to the head-to-head overlap of hybridized orbitals, that was the sigma bond. Okay? Well, if I have unhybridized p orbitals, that must mean that if I have, back to my ethene here, if I have this guy, these carbons can't hybridize all three of their p's because there has to be one left over that's not hybridized to use for the pi bond. So if I have an S and three p's over for this carbon, and an S and three p's for this carbon, they only hybridize an S and two p's, and that makes these carbons sp2 hybridized. On the test, here's the kind of question I am going to ask you. I am going to give you some big organic molecule like this, and I am going to say, label all the sigma and pi bonds, and then I'm going to say, tell me the hybridization. So, exactly one sigma between everything. Just like I said before, exactly one sigma. Everything else is a pi. So you would do that. Now the hybridization. This guy, since I had to mix 4 things together, is an sp3. Okay? It had to be the S and the 3 P's to make this an sp3. This guy only has 2 sigmas and 2 pi's. So it only had to merge 2 things together. That's sp. This guy also sp. This guy merged 3 things together, so that's sp2. Ditto this guy. One way you can always do this and always be right is to pretend everything's an sp3 and then subtract how many pi's there are from the 3. So here I say sp3, there are no pi's, so it's still sp3. This guy, I say sp3, there are 2 pi's, 3 minus 2 is 1, so that's sp. Ditto this guy. sp3 minus 2 pi's is sp. This guy, sp3 minus 1 pi, 3 minus 1 is 2, it's sp2. And this guy, sp2. Those are your only choices, sp, sp2, and sp3.